In last class, we discussed about Taylor series and Maclaurin series. So, we continue with the session Taylor series and Maclaurin series. Now, consider another problem. Find Maclaurin series of f of z is equal to cos hz. We want to find the Maclaurin series of cos hz. So, first we write f of z is equal to cos hz. And we know that cos hz is equal to cos iz. So, first we have cos z is equal to 1 minus z square by 2 factorial plus z raised to 4 by 4 factorial minus z raised to 6 by 6 factorial, etc. So, instead of z, we substitute iz. This implies cos iz is equal to 1 minus iz square divided by 2 factorial plus iz raised to 4 divided by 4 factorial minus iz raised to 6 divided by 6 factorial. This is equal to 1, and here my minus of iz square. This is equal to minus I square minus of minus implies plus. This is equal to plus, and z square by 2 factorial plus. Similarly, here I raised to 4 is equal to 1. This implies z raised to 4 divided by 4 factorial, and here is a minus, and I raised to 6 is equal to minus 1. This implies plus z raised to 6 divided by 6 factorial. So we get cos of hz is equal to 1 plus z square by 2 factorial plus z raised to 4 divided by 4 factorial plus z raised to 6 divided by 6 factorial, etc. Is it clear? Is it clear? Okay. Now move to another problem. Find the Maclaurin series of f of z is equal to sin hz. Here also we know that sin hz is equal to minus I sin iz, and we have sin z is equal to z minus z cube by 3 factorial plus z raised to 5 by 5 factorial minus z raised to 7 divided by 7 factorial, etc. So, instead of z, we substitute iz. So, sin of iz is equal to iz minus zi whole cube divided by 3 factorial plus zi raised to 5 divided by 5 factorial minus zi raised to 7 divided by 7 factorial. This is equal to iz plus here zi all power cube divided by 3 factorial implies z cube I divided by 3 factorial. Means here is an I and I cube equal to minus I. So this minus and minus I implies plus and z cube divided by 3 factorial into I. Plus similarly we get here zi whole raised to 5 divided by 5 factorial. Similarly, z raised to 5 divided by 5 factorial into I, etc. So, I sin iz is equal to I of iz plus z cube I by 3 factorial plus z raised to 5 I divided by 5 factorial, etc. Now, multiply I throughout the bracket. This implies we get z plus z cube divided by 3 factorial plus z raised to 5 by 5 factorial, etc. Is it clear? Here we add a negative. Sin hz is equal to minus of sin minus of I sin iz. This implies we get z plus z cube divided by 3 factorial plus z raised to 5 by 5 factorial, etc. Is it clear? We know that sin hz equal to minus of I into sin iz. Here I take I into sin iz and multiply throughout a negative value, we get z plus z cube divided by 3 factorial plus z raised to 5 divided by 5 factorial, etc. Is it clear? Okay. So we move to next problem section. Evaluate integral z square minus z plus 1 divided by z minus 1 dz, where C is the circle, mode z equal to 1 and mode z equal to 1 by 2. We want to show that the integral value of z square minus z plus 1 divided by z minus 1 dz, where first we evaluate through the circle mode z equal to 1, and second we evaluate the integral throughout the circle mode z equal to 1 by 2. So by our Cauchy integral theorem, we have integral f of z dz divided by z minus z naught is equal to f of z naught into 2 pi a. Compare with our integral z square minus z plus 1 divided by z minus 1, we get f of z is equal to z square minus z plus 1. And the singularity z minus 1 is equal to 0 implies z is equal to 1. So here the singularity z naught is equal to 1. Now first check the singularity z is equal to 1 or z naught is equal to 1 lie inside or outside the given circle mode z is equal to 1. We know that z naught equal to 1 lies on the circle mode z is equal to 1. So there exists a value of f of z naught. Now apply Cauchy integral formula to this. We get integral f of z dz divided by z minus z naught dz is equal to 2 pi I into f of z naught. We know that here f of z is equal to z square minus z plus 1. This implies integral z square minus z plus 1 divided by z minus 1 dz is equal to 2 pi I into f of 1. So now substitute 1 instead of z in f of z. We get f of z is equal to z square minus z plus 1. This is equal to f of 1 equal to 1 minus 1 plus 1. And this is equal to 1. That is integral z square minus z plus 1 divided by z minus 1 dz is equal to 2 pi I into 1. That is 2 pi I. So first on mode z is equal to 1, we get the integral value, integral z square minus z plus 1 divided by z minus 1 dz is equal to 2 pi I. Clear? Is it clear? Okay. Same way, what about the value of integral f of z? What about the value of integral z square minus z plus 1 divided by z minus 1 dz around the circle mode z is equal to 1 by 2? Please comment. The value of integral z square minus z plus 1 divided by z minus 1 dz around the circle mode z is equal to 1 by 2. What is the value? What is the value? First we check the singularity z is equal to 1 lie inside or outside the circle mod z is equal to 1 by 2, and you must we have z is equal to 1 lies outside the circle mod z is equal to 1 by 2. So we can conclude that integral value of z square minus z plus 1 divided by z minus 1 dz under Cauchy's theorem, the value of integral is, what is the value of integral? Please comment your answer. What is the value of integral? Here, mod z is equal to 1 by 2 implies our singularity z is equal to 1 lies outside the unit circle. Lies outside the circle mod z is equal to 1 by 2. This implies our f of z, z square minus z plus 1 analytic throughout the circle mod z is equal to 1 by 2. That means using Cauchy's theorem, we have integral z square minus z plus 1 divided by z minus 1 dz is equal to 0. Right? Is it clear? Please respond. We know that mod z is equal to 1 by 2 here. Singularity 1 does not belong to the circle mod z is equal to 1 by 2. That means our f of z is analytic throughout the circle mod z is equal to 1 by 2. This implies by Cauchy's theorem integral z square minus z plus 1 divided by z minus 1 is equal to 0. Is it clear? Please respond. Okay. Now, next question. Using Cauchy's integral formula, evaluate integral z dz divided by 9 minus z square into z plus I, where C is the circle mod z is equal to 2. We want to evaluate integral z dz divided by 9 minus z square into z plus I, where given C is mod z is equal to 2. So, first we check the singularity of the given function and check the singularity lies outside or inside the unit, outside or inside the given circle mod z is equal to 2, and compare with the Cauchy's integral formula and conclude the value. Please try to solve. I will give you 5 minutes. Please try to solve these integrals. What is the singularity of z divided by 9 minus z square into z plus I? Please comment. What are the singularities of 9 minus x square into z plus I? Minus I and minus I and how to find the singularity of this function? We equate with the 9 minus z square into z plus I equal to 0. And we just split z plus I is equal to 0 and 9 minus z square is equal to 0. In first, z plus I is equal to 0, we get z is equal to minus I, and 9 minus z square is equal to 0 implies 9 is equal to z square. This implies z is equal to plus or minus 3. Okay, the singularities are plus or minus 3 and minus I. Is it clear? Okay. Now, we check these singularities lies inside or outside the circle mod z is equal to 2. What are the singularities lies inside the circle mod z is equal to 2? What are the singularities? Which singularities lies inside the circle mod z is equal to 2? Is minus 3 lies inside the unit circle or 3 lies inside the unit circle? Not unit circle, mod z is equal to 2. Is minus 3 lies inside the circle mod z is equal to 2? Or is 3 lies inside the circle mod z is equal to 2? What are the singularities lies inside the mod z is equal to 2? Here, our circle mod z is equal to 2 and minus 3 and 3 are lies outside the circle mod z is equal to 2 and minus I lies inside the circle mod z is equal to 2. That implies here we have to consider only one singularity, that is minus I, and plus or minus 3 lies outside the circle mod z is equal to 2. So we can neglect these singularities for considering our integral z dz divided by z minus z square 9 minus z square into z plus I. So we have to rearrange these. First, here 9 minus z square into z plus I is equal to 0 implies z is equal to plus or minus 3 and plus minus I are the singular points, and plus or minus 3 does not belong to the circle mod z is equal to 2 and minus I belongs to the circle mod z is equal to 2. Take f of z is equal to z divided by 9 minus z square. Fix z plus I in the denominator and fix f of z is equal to z divided by 9 minus z square. This implies f of minus I is equal to minus I by 9 plus 1. This is equal to minus I by 10. That is f of z is equal to 9 by z. F of z is equal to z divided by 9 minus z square implies f of minus I is equal to minus I divided by 10. Now, our integral f of z divided by z plus I dz is equal to 2 pi I into f of minus I. This is equal to 2 pi I into minus I by 10. That is 2 pi into, here is an I and here is a minus I. So, minus of I square into minus 1 divided by 10. This is equal to I square equal to minus 1 and here is also a minus 1. So, multiply minus 1 and minus 1, we get 1 and 2 pi divided by 10. That is pi by 5. Pi by 5 is the integral value of integral f of z dz divided by z plus I. Is it clear? Here we must find the singular points, and the singular points are lies inside or outside the unit circle. Check must. And we know that here minus I is the singular point that belongs to the circle mod z is equal to 2. So fix z plus I in the denominator of the integral and make or fix f of z is equal to z divided by 9 minus z square. Now find the value of f of minus I. So substitute minus I instead of f of z in f of z, we get minus I divided by 9 plus 1, this is equal to minus I by 10. And now substitute these values in the Cauchy's integral formula, we get 2 pi I into f of minus I. This is equal to 2 pi I into minus I by 10, and we conclude that the integral value is pi by 5. Is it clear? Is it clear? Boys, is it clear? Boys, Adil, Vaishnav, Vishnu, Sheep, Dominic, Akshay, Ashwin. Okay. Now move to next problem. Integral cos h of pi z divided by z into z square plus 1, where c is the circle mod z is equal to 2. We want to find the integral value of integral cos h of pi z divided by z into z square plus 1, where c is the circle mod z is equal to 2. First, we check the singular point of this function, that is z into z square plus 1 is equal to 0. This implies z is equal to 0 and z is equal to plus or minus I. These are the singular points of cos h pi z divided by z into z square plus 1. And we know that z is equal to 0 and z is equal to plus or minus I, or lies inside the mod z is equal to 2. So we split the integral at z is equal to 0, z is equal to pi and z is equal to minus I, and add these three integral values, we get the integral of cos h of pi z divided by z into z square plus 1 dz. First we consider z is equal to 0 is the singular point of this function. So fix z in the denominator and make to fix all the other terms as f of z. Here f of z is equal to cos of h pi z divided by z square plus 1. And similarly, here I is the singular point, so minus I is the singular point, so fix z plus I in the denominator and fix f of z is equal to cos h of pi z divided by z into z minus I. Similarly, we choose z is equal to I is the singular point, so fix z minus I in the denominator and make other all terms as f of z in numerator, cos h of pi z divided by z into z plus I dz. Now compare with our Cauchy's integral formula and substitute these values, we get the answer. Here f of z is equal to this selected portion, here f of z is equal to this selected portion, and f of z is equal to this selected portion. So this is equal to 2 pi I into cos of h of pi z divided by z square plus 1 at z is equal to 0 in first integral, and next integral 2 pi I into cos of h pi z divided by z into z minus I at z is equal to minus I, and the last integral 2 pi I into cos of h pi z divided by z into z plus I at z is equal to I. I take 2 pi I outside and other terms as here represented. And now substitute z is equal to 0 instead of z in first equation, and z is equal to minus I instead of second equation, and z is equal to I instead of third equation, z in third equation. So here cos h of pi z divided by z square plus at 0 is equal to 1, and here this is equal to 1 by 2, and here this is equal to 1 by 2. That is, we know that cos of h pi z divided by z square plus 1 is equal to, at z is equal to 0 means we take the value 0 at z, that is equal to cos of h into 0 divided by z square plus 1, that is 0 plus 1. And we know that cos of h0, that is cos 0, this is equal to 1, and 0 plus 1 is equal to 1, that is 1 by 1 is equal to 1. And now cos of h pi z divided by z into z plus I. We know that cos of h pi z is equal to cos I pi z. And substitute cos I pi z instead of cos h of pi z. So our function is cos I pi z divided by z of z plus I. Now substitute the value at z. Here z is equal to minus y. We substitute the value, z is equal to minus I. We get, z is equal to 1. We substitute the value z is equal to I. We get cos I into pi into I divided by I into pi plus, I plus I. That is cos of, here I, and here is also an I, so I square is equal to minus 1. That is cos of minus pi divided by I into 2y. That is cos of minus pi is equal to cos pi, so I write cos minus pi as cos pi, and denominator I into I is equal to minus 1, that is minus 2. This is equal to minus 1 by minus 2, means cos pi, we know that the value of cos pi is equal to minus 1, so minus 1 divided by minus 2 equal to 1 by 2. Similarly, cos of h pi z divided by z into z minus I equal to cos I into pi z divided by z into z minus I. Here the singularity is minus I, so substitute the value minus I instead of z. We get cos of I pi minus I divided by minus I into minus I minus 1. This is equal to I into minus I becomes 1, and cos pi divided by minus 2 pi, so 2y into I. That is cos pi is equal to minus 1, so minus 1 divided by minus 2. This is equal to 1 by 2. So substitute these values 1, 1 by 2 and 1 by 2 in our equation. We get 2 pi I into 1 plus 1 by 2 plus 1 by 2. That is 2 pi I into 1 plus 1. That is 2 pi I into 2 implies 4 pi I. Is it clear? Is it clear? Please comment your answer. Okay. Last part. We split our integral 2 pi I into the whole term. Okay, now we want to find all the three terms instead of z is equal to 0 and z is equal to minus I and z is equal to I. So first take the value of cos h pi z divided by z square plus 1 at z is equal to 0. That is cos h pi z divided by z square plus 1. Here our singularity is z is equal to 0. So substitute z is equal to 0 in our equation. So cos h into 0 divided by 0 plus 1. That is cos h0 means cos of 0 equal to 1 and 0 plus 1 equal to 1. This is equal to 1 by 1 equal to 1. Similarly, our next integral here f of z is equal to cos h pi z divided by z into z minus I. Here the singularity is z is equal to minus I. So we substitute z is equal to minus I in our equation. That is cos of h pi z divided by z into z plus I is equal to cos of I into pi z divided by z into z plus I. Here this is a result. Cos of Iz is equal to cos hz. We already know that cos of hz is equal to cos Iz. Here there exists a pi also. So cos of h pi z is equal to cos of I into pi z. And I choose cos h pi z instead of I choose cos I pi z instead of cos h pi z. So our equation becomes cos I pi z divided by z into z plus I. This is equal to cos I pi I divided by I into 1 plus I equal to cos of minus pi divided by I into 2 pi. Here this is the third part of our equation. So z is equal to I is the singular point. So I cos h of pi z divided by z into z plus I is evaluated to z is equal to I. Here instead of z is equal here instead of z we substitute z is equal to I and we get cos pi divided by minus 2 that is equal to minus 1 by minus 2 equal to 1 by 2. Similarly, we consider the second integral. Here z is equal to minus I is the singular point. So we substitute z is equal to minus I instead of z. So we get, on rearranging, we get cos pi divided by minus 2y into minus I. That is equal to minus 1 by minus 2 equal to 1 by 2. So we get all the three integral value all the three f of z value at z is equal to 0, z is equal to minus I and z is equal to 1. So now substitute all the three values, we get 2 pi I into 1 plus 1 by 2 plus 1 by 2. That is 2 pi I into 2 implies 4 pi I. Is it clear? Okay. Now move to another problem. Here evaluate z divided by z square minus 1 dz around the unit circle. Around the circle mod z minus I equal to 2. Evaluate. So we want to evaluate integral z divided by z square minus 1 dz around the circle mod z minus I minus z minus 1 minus I is equal to 2. So by our Cauchy's integral formula, we know that f of z naught is equal to 2 pi I integral f of z dz divided by z minus z naught. This implies integral f of z dz divided by z minus z naught is equal to 2 pi I into f of z naught. Now consider our equation here. z square minus 1 is in the denominator. So we first find the singularities of the given function, that is singularities equal to z square minus 1 equal to 0 implies z is equal to plus or minus 1 on mod z minus I minus z minus 1 minus I equal to 2. Now we want to check that these values plus or minus 1 lies inside or outside the unit circle. We substitute 1 instead of z in the equation mod z minus 1 minus I is equal to 2 and find the value. Similarly, we substitute z is equal to minus 1 instead of z in mod z minus 1 minus I is equal to 2. So, first I put z is equal to 1. This is implies z minus 1 minus I implies 1 minus I. This is equal to, here 1 and minus 1 cancel each other, and in modulus we get mod minus I equal to 1, that is less than 2. That means z is equal to 1 lies inside the circle mod z minus 1 minus I is equal to 2. Similarly, we check z is equal to minus 1 lies inside or outside the circle mod z minus 1 minus I is equal to 2. So put z is equal to minus 1 in equation, we get minus 1 modulus of minus 1 minus I is equal to modulus of minus 2 minus I. That is, modulus of minus 2 minus I is equal to square root of 2 square plus 1. We know that modulus of x plus iy is equal to root of x square plus y square. We use this result here. So we get modulus of minus 2 minus I is equal to root of 2 square plus 1. That is, root of 4 plus 1 is equal to root 5, which is greater than 2. So we get z is equal to minus 1 lies outside the circle mod z minus I minus 1 is equal to 2. So we fix z minus 1 in the denominator and choose all other terms as f of z and evaluate using our Cauchy's integral formula. That is, integral z dz divided by z square minus 1 is equal to integral z divided by z plus 1 divided by z minus 1 dz. Here f of z is equal to z divided by z plus 1. So substitute z is equal to 1, we get 2 pi I into f of 1, that is 1 divided by 1 plus 1, that is f of 1 is equal to 1 by 2. That means 2 pi I into 1 by 2 equal to pi I. Is it clear? So our integral value of integral z divided by z square plus 1 is equal to pi I. Is it clear? Voice, is it clear? Okay. So attendance please. Roll number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12. Okay, 11 and 12 are absent. Okay, thank you.